Hi, I'm Fernando Pereira from UFMG, and today we continue talking about loop optimizations. We shall talk about induction variables in particular. These are the variables that control the iterations in the loop. Induction variables are the counters that we increment or decrement in every loop. There are two kinds of induction variables. Basic induction variables are variables whose definition is based on themselves, plus or minus some constant. They are called induction variables because of this inductive definition, like I equals I itself plus something. And then we have derived induction variables, which are variables that are defined from some induction variable, either via multiplication or via addition to some loop invariant expression. As an exercise, can you try to spot the basic and derived induction variables in these loops? Would you like to stop the video and think about it? Well, I is a basic induction variable in both the loops. Then J is a derived induction variable once we split its definition into two instructions, which are an addition and a multiplication. That becomes easier to see, actually. One of the most well-known optimizations that we can do with induction variables is strength reduction. Strength reduction is a code transformation that replaces one or more instructions with other instructions that are likely to be cheaper in a given target architecture. The most typical example is replacing multiplication with addition when defining derived induction variables. For instance, can you think about how we could replace the multiplications with additions in these two programs? We have multiplication here on the left, and here both define variable j, which is a derived induction variable. You can see the transformed programs on the right. Notice that in both cases we have created auxiliary variables, the j-axis in the figures, that we use to replace the multiplication. Let's see how to implement this optimization systematically. We can perform the replacement in three steps down in the figure. These steps refer to the instruction j equals I times c, where I is an induction variable with step b. Basically, we move the invariant product a times c outside the loop. Let's call it j prime. Then we add an increment to it in the loop. Let's call this instruction j prime equals j prime plus c times b. Notice that c times b, we can move it outside the loop, for both c and b are invariant. Then we replace j with j prime. Let's see how that goes with an example. In the top, we have the original program. We initialize the auxiliary j prime with a times c outside the loop. Then we create the product c times b here, also outside the loop. Then we add an instruction to increment j prime with this product, which we call t prime, for instance. Then we replace j with j prime, and we are done. Let's apply its optimization in this program on the right. Look at it. Can you find the basic and derived induction variables that this program contains? I is a basic variable. J is derived from I. K is also derived. K is derived from J, which is itself an induction variable, also derived. Now we need to create auxiliaries to replace J and K, and we need to think about how we should initialize these auxiliaries. And also we need to think about how we should increment these auxiliaries. Would you like to stop the video and think about it? You might go back a few slides to read the replacement algorithm again. Here on the right, we see the new program with instructions to initialize j prime and k prime. These instructions are in the first block right here. We also have instructions to increment j prime and k prime at the bottom of the program right here. And then we see that the multiplication has disappeared. We are now just incrementing j prime and k prime, but there are some obvious optimizations that we could apply to this program. Can you think about them? First, variable j is no longer used in this new program. We can simply remove it. Interestingly, j prime is only used in the definition of itself. Thus, we can also remove it. Can you figure out what happened? J was used in the original program, but now it's no longer used, and neither is j prime. Why is that so? Another thing that we can do is to remove what we call almost useless variables. A variable is almost useless if the only thing that it does is to control the number of iterations in the loop. In this case, we can remove it as long as there are other induction variables in the loop. Let's see how we can do it with variable I in this example. Think about these two questions in the video. These are important questions. Stop the video, pick up a piece of paper, and try to rewrite the comparison to avoid using I. You can use k prime instead. You can write I as a function of k prime. We have that k prime equals I times 4 plus a, and I is used in the comparison. So we can rewrite I as a function of k prime as I mentioned before. In this case, the comparison will use only k prime instead of I. In the end, we will get the program on the right, which no longer contains variable I. Look at this program on the right. Is there any other optimization that we could apply onto it? We can eliminate the variable k. It's basically a copy of k prime. So let's keep only k prime, and then we get this program on the right. How could we apply loop inversion in this program? Can you do it? That would save you one go-to, actually. So on the right, I have the program after loop inversion. We see that the branch now exists only at the end of the loop. And here you have the original and the final optimized program. The optimized program has a shorter loop body, and the instructions are also more efficient after strength reduction. Could you try to estimate by how much the program on the right is likely to outperform the program on the left? I shall leave that as an exercise. A final optimization that we shall see is loop unrolling. Loop unrolling is a very effective optimization, actually. It merges successive iterations of a loop into a single iteration by replicating the body of the loop. It has some benefits. The first, of course, is to eliminate the dynamic execution of some conditional tests. But more than this, unrolling creates large basic blocks, which are easier to optimize. It's always easier to optimize straight-line code. Let's see how unrolling works on this program on the right. We start replicating the body of the loop. We shall apply an unrolling factor of 2. On the right, we see the loop with the replicated body. Then we merge these two bodies. To do this, we remove the branch at the end of the first body and doubles the increment of the induction variable. But then we have a problem. What if the loop runs an odd number of iterations? We have 2 bodies per iteration now. What should we do? The answer is simple. We create either an epilogue or a prologue to the loop. Here we have the version with an epilogue. The epilogue runs the iterations that are not covered by the enrolled version of the loop. And with loop unrolling, we close this class. Here we have a few papers that describe some of the optimizations that we had seen during this class. In the next class, we shall start talking about static single assignment form, which is a super cool idea in compilers, and that uses the notion of dominance that we introduced in the first class on loop optimizations. Thank you.